The system bus is the communication pathway that connects the CPU with memory and other devices. Subsets of bus line carry control signals, address signals, data signals, and electrical power. The number and use of these lines, as well as the procedures for controlling access to the bus, are called the bus protocol. A master-slave bus protocol is simple to implement, but a peer-to-peer bus protocol improves computer system performance. Subsidiary buses that connect a subset of system components are also used to improve performance. Bus clock rate. One clock cycle equals one transfer of command information, data, or both. The send activates or sends data or commands for one cycle. The receiver has one cycle to recognize the message and read its content, typically transferring it to some internal buffer. The clock is a common timing reference that coordinates the activities of sending and receiving devices. As with CPU clock rates, cycle time is computed as the data transfer rate of a bus is computed as bus DTR, which equals data transfer unit, size times the clock rate. Data transfer rate can only be increased by increasing the clock rate, increasing the number of bits transmitted per clock cycle, or the data transfer unit size, and using a more efficient bus protocol. The CPU communicates with peripheral devices through I/O ports. The CPU and bus interact with all peripheral devices by using simple data movement instructions. The CPU treats each peripheral device as though it were a storage device with a linear address space. The device or its controller translates access commands to the linear address space into whatever physical actions are necessary to perform the access. A peripheral device controller performs several important functions, including logical to physical translation, physical bus interface, sharing a single bus connection between multiple devices, and, optionally, caching. The storage locations of the hypothetical device is a linear address space, a sequence of storage locations numbers starting with a 0. A read, device to CPU, or write, CPU to device operation is called a logical access. The device or a device controller translates logical accesses into physical accesses. The translation specifics vary depending on the device specifics. Application programs use interrupt processing to coordinate data transfers to or from peripheral devices, notify the CPU of errors, and call OS service programs. An interrupt is a signal to the CPU that some condition requires its attention. When an interrupt is detected, the currently executing process is suspended by pushing current register values onto the stack and transferring control to the corresponding interrupt handler. When the interrupt handler finishes executing, the stack is popped, and the suspended process resumes execution from the point of interruption. A buffer is a region of memory that holds a single unit of data for transfer to or from a device. Buffers enable devices with different data transfer rates and unit sizes to coordinate data transfer efficiently. A cache is a large buffer implemented in a device controller or primary storage. When used for input, a cache enables more rapid access if the data being requested is already in the cache. The cache controller guesses what data the CPU will request next and loads this data into the cache before it's actually requested. Cache differs from a buffer by reading from a cache doesn't consume the data. A cache is used for bidirectional data transfer, and a cache is used only for storage devices. A cache is usually much larger than a buffer. More intelligence is required to manage cache content, and cache-related performance improvements depend on cache size and cache management intelligence. Compression reduces the number of bits required to encode a dataset or stream, effectively improving performance by increasing the capacity of a communication channel or storage device. A compression algorithm can be lossless or lossy. With lossless compression, data is exactly the same before and after compression and decompression. With lossy compression, some information is lost during compression and decompression. Data compression requires increased processing resources to implement compression and decompression algorithms, but it reduces the resources needed for data storage and communication. Computer system computational capacity can be increased with parallel processing techniques, including multi-core processors, multiple processor architecture, and clustering. A multi-core processor includes multiple CPUs and shared memory cache in a single microchip. Multiple processor architecture uses multiple single-core or multi-core processors sharing main memory and the system bus in a single motherboard or computer. Clusters connect computer systems with high-speed links. Each computer in a cluster works on part of a large problem and exchanges data as needed. We have explored how data is transmitted between computer system hardware devices. We have looked at the hardware and software techniques for improving data transfer efficiency and, therefore, overall computer system maintenance.